This is Magic 063, Differentiable Manifolds. I'm Kirill Mackenzie, and this is the podcast on vector fields. Here's the definition. A vector field on a manifold is a smooth map, capital X, defined on M, taking values in the tangent bundle such that at each point, capital X is in the tangent space at little m. So in other words, we have a selection of tangent vectors at each point of the manifold, and this depends smoothly on the point little m in the manifold. A couple of points about notation. In previous podcasts, I've often used capital X to indicate a tangent vector, and it's often very important to keep clearly distinct whether something is a tangent vector or a vector field. So from now on, normally capital X by itself will be a vector field. And if I want to indicate an actual tangent vector, I'll write X subscript M, where M is the point that the vector is tangent to. So the actual value of a vector field at a point will just be X brackets M as for any function. We'll talk about how important this distinction is in a little while. So, vector fields. First of all, they can be added pointwise, and there is a bracket missing here, which I will now insert carefully. The sum of two vector fields, x plus y, at a point m is just the sum of x at m plus y at m. Pointwise addition. Multiplication by a scalar, again, that's pointwise multiplication by a scalar function. That's a function f on the manifold. I haven't actually spelt that out, so let's do that now. F is a smooth function on M. And this makes the set of all vector fields into a module over the algebra of smooth functions. We'll prove later on, or at least we'll see how to prove, that this module is actually finitely generated and projective. And that means that it's about as close to a vector space as it's possible to be, given that for the vast majority of manifolds, the set of vector fields certainly doesn't form a finite dimensional vector space. But finitely generated and projective is a good second best. We'll come to that later. Right now, just notice, first of all, that, of course, there is always the zero section. So vector fields always exist. That's trivial. At the other extreme, it's quite possible to have a manifold for which there's no vector field which is never zero. In other words, for which every vector field has at least one zero. And a simple example of that is the sphere S2, and we'll see that in due course when we look at that example in detail. But there's no vector field on S2 which is non-zero everywhere. On the other hand, we'll also prove that given a point, for any manifold, given a point m0, and given a tangent vector, at that point, there exists a vector field which has that value. Okay, and we'll prove that, or at least go through the broad steps of the proof later on. So, in fact, vector fields are very numerous, and it's generally quite a large module. So, next, vector fields operate on smooth functions. We already know that for individual tangent vectors, but a vector field is able to act on a smooth function at every point. So take a vector field x, take a smooth function f on M, and define a function x brackets f on M like this. So x of f at a point M is the tangent vector x at M applied to f. Okay? And that's smooth. In fact, one can define smoothness for x in terms of this condition. If I take a map capital X from M to Tm, such that each value of capital X at a particular point little m is in the tangent space at M, but I don't assume any smoothness condition. And if I find that this operation of x on the smooth functions always goes from smooth functions to smooth functions, then in fact x was a smooth map from x to Tm. So the main thing is that x, this operation of applying x to smooth functions, sends smooth functions to smooth functions. I'm calling this a Lie derivative. This is really stretching terminology a little bit. We'll talk about Lie derivatives later on, and you'll see then that this is the very simplest possible case of a Lie derivative, and in fact it doesn't have some of the characteristic properties that make Lie derivatives firstly interesting and secondly rather tricky. But it is useful to have a separate name, because bear in mind what we've got now are two distinct ways of thinking about a vector field. We can think about it as a map from M to Tm, a smooth map with that property that it's right inverse to Tor, or we can think about it as the Lie derivative. In fact, it's a differential operator on the smooth functions on M. And these 2 points of view are equally important. And I'll sometimes write Lx, L for Lie, L sub x, in order to signal that I'm talking about the operator, not the map from M to Tm. So then Lx, as an operator on functions, has three properties that basically come from the corresponding properties for tangent vectors. First of all, applying x to a product of functions gives a kind of product rule. Secondly, x is additive. And thirdly, x is linear over the reals. So a there is just a real number or constant function, if you like. And then there's an important result that these three properties characterize the differential operators or the Lie derivatives that come from vector fields. Namely, if x is a map from smooth functions to smooth functions, and it satisfies these three conditions of equation 8, then x is, or perhaps we should be more careful and say x corresponds to, a unique vector field on M. Now, if I take two vector fields x and y and I take their composition, the result will involve second order derivatives, and it won't satisfy the conditions of equation 8. However, if I take x composite y and subtract off y composite x, then I do get an operator that satisfies the conditions on 8. So this defines a vector field, another vector field, and this is usually written with square brackets, x comma y, and this is the Lie bracket of x and y. This is something that's absolutely fundamental to work with manifolds. It will come up repeatedly, probably in every podcast, or almost every podcast. I'll talk about properties in a moment, But first of all, if we're on Rn, and we might have vector fields like this as linear combinations of the partial derivatives, and the coefficients here, the xi and the yi, are of course functions on Rn, and of course that word there is meant to be and. Then the Lie bracket of x and y is given by this formula here. And that's a straightforward calculation. Now the Lie bracket has two straightforward properties. It's bilinear over the reals. That's very easy to check. And it's skew symmetric. Again, very easy to see. It has then two further properties that are named. This first one, which I'm sure you've probably seen in some context or other, is the Jacobi identity. And the second one is called the Leibniz identity. And this is for what happens when you're taking a Lie bracket and you multiply one of the terms in the brackets by a smooth function. The bracket is bilinear over the reals. It isn't bilinear over functions. You get these Leibniz terms here. And of course, if I put a g in front of the x instead of an f in front of the y, then I could get a corresponding formula just by using skew symmetry. These are easy to prove. I'll outline the proof of Leibniz. What's necessary is to apply both sides of the equation to an arbitrary function g. So I take a smooth function g in M and I apply the left-hand side to it. And the Lie bracket, of course, is x of fy of g minus f times y of x of g. And now this first term involves the product of functions. F is one function, the other one is y of g. So I take the f outside and multiply it by x of y of g. And then I take the yg outside and multiply by x of f. And the last term I leave as it is. And now I've got an f outside the first term and an f outside the second term, so I group those together. And in fact, once I've taken the f outside, I've got x of y of g minus y of x of g. So that is just the Lie bracket of x and y applied to g. And then here's y of g times x of f. And the g, of course, is the variable, so let's write x of f first. And then y. Let's just fix that up. X of f by y of g. So this is true for all g, and so I can remove that and say that the Lie bracket of x with fy is equal to f times xy plus xf times y. Okay. Jacobi, of course, means that what we've got is a Lie algebra. But there's two comments to make about this. First of all, if we're talking about a Lie algebra over the reals, then for almost any manifold, the module of smooth functions will be infinite dimensional as a real vector space, and so it will be an infinite dimensional Lie algebra. That's okay. Infinite dimensional Lie algebras are studied and quite a lot is known about them, but after all, the fact that this is a module over the smooth functions is a crucial part of the situation, and neglecting that is throwing away quite a lot of interesting structure. So while it's perfectly valid to regard the set of vector fields as a Lie algebra, it's only giving part of the story. The Leibniz identity is important too. So just to recap, vector fields may be regarded as smooth maps from X into the tangent bundle, from X from the manifold M into the tangent bundle, which are right inverse to tau. And secondly, they may be regarded as differential operators on smooth functions that satisfy the conditions 8. And there's a third description in terms of flows. We'll talk about that later. That's equally important with these first two descriptions. But that's all for now.